Hello, my name is Arthur Rodriguez. I am in my last year of General Engineering School in France, specialized in system control and signal processing. I have been the team captain on this project, and I also work on the path planning algorithm.
Hello, I'm Valentin Zentag, and I am in my last year of General Engineering School in France, specialized in applied artificial intelligence, and I've been a team member on this project. I mainly worked on the image processing algorithm.
Hello, my name is Romain Martin. I am a last year engineering student specialized in control systems. I'm a part of this team and I mainly work on the drone controller.
The outline of this presentation is the following. Firstly, we will detail the algorithm structure. The latter is divided into two main parts, the image processing system and the path planning strategy. We will then focus on the results on the controller tuning. Finally, we will mention the main challenges that we faced and how we tackled them. The algorithm structure consists of two main parts, the image processing system scheduled at 200 milliseconds and the control system scheduled at 5 milliseconds. The image processing system can be divided into three main parts, an image masking strategy, the path detection algorithm, and the target detection algorithm. The control system consists of an estimator and a controller which were already given, and the path planning algorithm that we designed. Finally, here are the interactions between the different modules.
As far as the image processing is concerned, the top right animation shows the drone in a 3D environment. The top left animation depicts the image acquired by the drone camera, with the white and blue points corresponding to the drone and gold point positions respectively. The bottom left animation shows the masked path, as well as the reconstructed line segments by the drone. Finally, the bottom right animation shows our processing logic. In this first situation, only one line segment is visible. This is confirmed by a linear regression on the green points of the bottom right animation. In this case, the gold point is set ahead of the drone at a fixed distance. In this second situation, at least two line segments are detected. An iterative linear regression process confirms that two line segments are detected, and the goal point is then set to be the intersection of these two line segments to avoid any corner cutting. Finally, the landing target is detected as being the only masked cluster fully visible on the image. This assumption is validated given the flight altitude and the camera field of view. In this case, the goal point corresponds to the barycenter of the cluster.
As far as the path planning strategy is concerned, its main state machine is divided into 5 steps. The first state is the takeoff state, during which the drone gains altitude until reaching the target altitude of 1.1 meter. Once this altitude is reached, the drone enters the path following state. During this state, the goal point provided by the image processing system is filtered in order to provide a smooth target to the controller. The drone speed is also modulated in case an intersection is detected. This state remains active until the landing target is detected. Once the landing target is detected, the drone centers on the landing target and stabilizes itself. Once centered on the target and stabilized, the drone starts its landing phase. When the drone has landed, the simulation is stopped.
As far as the controller is concerned, it can be seen that the initially provided controller is good enough to satisfy the accuracy criteria. It indeed keeps the drone within 3 cm from the track center line. However, given that each side of the track center line is 5 cm wide, it means that there is a 2 cm margin in terms of accuracy. We therefore try to optimize the controller performance from the two following perspectives: making the drone as fast as possible while keeping the drone within 5 cm from the track center line. At the end of the day, the precision criteria is the optimization constraint of the drone speed. The controller has been optimized on specifically designed controller tuning environment as long as the image processing system was under development. Moreover, the track used were representative of the extreme scenarios such as sharp or right angles or even very long straights. In terms of time, this optimized controller enabled a 60% improvement compared to the initial one.
Among the different challenges we faced, here are the most demanding ones. The fact that the camera is attached to the drone body and not permanently facing down introduced some goal point position error. A geometric correction factor has been designed to address this issue. The estimator precision introduces drift compared to the real drone position. However, given that the goal point and landing target coordinates are computed relatively to this estimated drone position, the impact of the drift is mitigated. We also faced some real-time constraints related issue. Indeed, the goal point provided by the image processing systems needs to be filtered to smoothen the steps introduced by the scheduling rate difference between the image processing system and the control system. In terms of accuracy, the integral component of the controller was introducing some drift when switching from one segment to another. This issue has been addressed by resetting the integrator value when changing from segments.
Let's finish on an animation showing our simulation results compared to the exact path on the left and the reconstructed path on the right. Thanks for your attention.